This is the brief on covariant derivatives and metric geometry. We're diving into, the mathematical language we need for physics when spacetime itself is curved. It's all about making sure our math can separate what's actually happening from misleading artifacts caused by our coordinate system. First up, the main job of the covariant derivative is to distinguish real, physical change, like a vector twisting in space, from what just looks like change because your coordinate system is rotating. See, the regular old partial derivative? It can be fooled. It might tell you nothing's changing when, in reality, the physical object is twisting. The covariant derivative is what gives you the real story. Second, for the geometry to even work, there are two non-negotiable rules. The first is scalar equivalence. A scalar is just a number, like temperature, right? It doesn't have a direction, so its complex derivative has to equal the simple one. Simple as that. Then there's metric compatibility. This is huge. It basically just says that when you move vectors around in curved space, their fundamental properties, like their length and the angle between them, have to stay perfectly the same. And finally, this derivative isn't some weird, isolated tool. It plays by the rules we already know, like the product rule, even with really complex tensors. This is so important because it means it fits right into the established structure of our mathematics. Understanding the covariant derivative is absolutely essential for ensuring our descriptions of curved spacetime are both mathematically consistent and reflect physical reality.